It is quite possible to have multiple parts in a simulation that interact with one another. Often this interaction involves contact between these parts. Other times you might have a single part with different regions that contact each other, what we call self-contact. In this tutorial, I'll explain the basics of contact, and we'll show how you can include contact interactions in your simulations. The setup consists of three parts: a plank, a block with a semicircular surface on one side, which I shall refer to as the curved block, and a block with flat surfaces, which I shall refer to as the rectangular block. The curved block is fixed on the bottom, and the plank is fixed at one end, making it a cantilever. A force is applied on the free end of the plank, pushing it downward so that it bends around the curved block. At the same time, the rectangular block holds the top surface of the plank flat, preventing it from arching upwards. The dimensions of the parts are displayed in the figure. The plank is made of aluminum 2024 T3 with a mass density of 2,770 kilograms per meter cubed, a Young's modulus of 73.1 gigapascals, and a Poisson's ratio of 0.33. The rectangular and curved blocks are made of AISI 1005 steel with a mass density of 7,872 kilograms per meter cubed, a Young's modulus of 200 gigapascals, and a Poisson's ratio of 0.29. Abaqus does not check to see if parts are coming in contact unless specifically told to do so. One way to do this is to use the contact pairs method. Here we tell Abaqus which surfaces are likely to come in contact so it can keep track of these. The other is the general contact method, which will be covered in a subsequent tutorial. The contact pairs method requires two steps. First, you create a contact interaction property. Here you can provide information such as the tangential behavior properties, the friction coefficient, the friction formulation, the critical shear stresses, and so on. You can also specify the normal behavior and a number of other mechanical and thermal properties of the contact interaction. After that, you create the surface-to-surface interaction itself. Here you define the actual surfaces that will come in contact, the master-slave relationship between them, and set options such as the discretization method and the sliding formulation. We'll explain all of these terms over the course of the tutorial. We will have contact in two regions. The first is between the plank and the curved block. We will make this interaction frictionless. The second is between the rectangular block and the plank. Here we will specify a friction coefficient of 0.1 and we'll tell Abaqus it is isotropic, meaning that the friction coefficient is the same in all directions. The analysis will be carried out in three steps: the initial step, a make contact step, and an apply force step. Contact is a severely discontinuous nonlinearity. By having a separate step to establish contact, we make work a little easier for the solver and prevent chatter, thereby reducing the number of iterations required to solve the analysis. We will talk more about this in the course of the tutorial. So let's get started. Open a new model in Abaqus. Rename it Contact Simulation. Create a new part named Plank, which is a 3D deformable solid extrusion. Set the approximate size to 20. Use the Create Lines Rectangle tool and the Add Dimension tool to sketch the part. Create another part called Curve Block, which is also a 3D deformable solid. Use the Create Circle Center and Perimeter tool to draw a circle which will form the top of the part. Use the Create Lines Rectangle tool to draw a rectangle that will form the lower half. Use the Auto Trim tool to trim out the parts of the circle and rectangle that are in the interior, leaving just the profile of the part. Create a third part called Rectangular Block, also of type 3D Deformable Solid Extrusion. Create the material AISI 1005 steel. Give it a mass density of 7,800 kilograms per meter cubed. For its elastic properties, set the Young's modulus to 200 gigapascals and the Poisson's ratio to 0.29. Create another material, aluminum 2024 T3. Set the mass density to 2770 kilograms per meter cubed. The Young's modulus is 73.1 gigapascals, and the Poisson's ratio is 0.33. Create a solid homogeneous section called steel section. Assign it the steel material. Create another solid homogeneous section called aluminum section and assign it the aluminum material. Assign the steel section to the curved block and the rectangular block, and the aluminum section to the plank. It's time to assemble the parts. Create a dependent instance of the plank. Then create an instance of the curve block. By default, Abaqus positions instances in the assembly at the same coordinates as the local coordinates of the part. Since both our parts were created at the origin, they overlap each other in the assembly. Hence check Auto Offset from other instances and Abaqus will automatically move the new part instance to a suitable location. Let's create assembly constraints for these two part instances using the Create Constraint Face-to-Face tool. It might be hidden behind the Create Constraint Parallel Face tool. Abaqus prompts you to select the planar face or datum plane of the instance that will be moved. Select the bottom face of the curve block. Abaqus then prompts you to select the planar face or datum plane of the instance that will remain where it is. Click the bottom face of the plank. Abaqus will display arrows on both faces. It will inform you that the instances will be constrained in such a way that the arrows point in the same direction, and will give you the option to flip it. Since the arrows for the correct faces are already pointing in the same direction, we can click OK. Set the distance between the two faces to 25 meters. This is the height of the curve block, hence the plank will lie on top of the curve block, or more accurately on a plane tangent to the top of the curve block. Once again, use a face-to-face constraint to move the part instance along the x-axis and align the side face. Set the distance to 30. It turns out the positive axis lies in the direction of the arrows, and we have moved the curved instance 30 meters in the wrong direction. We should instead have set it to -30. So right-click on Face-to-Face 2 in the Position Constraints container in the model tree and choose Edit. Set the clearance to -30. This fixes the problem. Use face-to-face constraints a third time to finish aligning the parts. Instance the rectangular block into the assembly and once again use face-to-face constraints to position it in the assembly. We shall now create the analysis steps. As discussed in the overview video, we will have 3 steps: initial, make contact, and apply force. The reason for having a separate step is because contact is a severely discontinuous nonlinearity. Changes in contact conditions lead to what are known as severe discontinuity iterations of the solver, as Abaqus standard attempts to establish the conditions of the contact surfaces. If contact is not fully established, the contact status may oscillate between open and closed, which is known as chattering. It is best to establish contact between the components in a reasonably smooth manner, avoiding large overclosures and rapid changes in contact pressure, and one way to do this is to include more steps in the analysis to move the components into contact before fully loading them. This makes setting up the model a little harder, but the solution will be much more efficient. The part instances that are in contact have been placed face-to-face in the assembly. There are two ways to establish the contact. The first is by applying a small force on one instance to bring it in contact with the other. The second option is to use a boundary condition to displace one part closer to another by a small amount to bring them in contact. We use the second option. Create the step called Make Contact. Set the type to Static General. The total time period of the step is set to 1. In the Incrementation tab, set the initial increment size to 0.1. This is because we are establishing contact in two regions at once, so the solver may have some difficulty setting the contact state. We turn on NLGEOM to include the effects of geometric nonlinearity. Create a second static general step called Apply Force. Once again, set the total step time period to 1 and the initial time to 0.1 in the Incrementation tab, since the simulation is quite nonlinear and a large step size would result in many unsuccessful iterations and cutbacks. Next come the boundary conditions. We will create 5 boundary conditions. They are Fix Curve Block, Fix Plank End, Fix Rectangular Block, Press Plank Curved, and Press Rect Plank. Fix Curve Block fixes the bottom of the curve block as if it is mounted on some other structure or positioned on the floor. Fix Plank End fixes one end of the plank, making it a cantilever that will bend around the curve block. Fix Rectangular Block fixes one end of the rectangular block, holding it in place so that one end of the plank remains held in position by it. Press Plank Curve displaces the plank downward by a distance of 0.2 meters to ensure that contact is established between the plank and the curve block. Press Rectangular Plank displaces the rectangular block downward by a distance of 0.21 meters to ensure that contact is established between the rectangular block and the plank. Let's go ahead and create these. We won't worry about associating them with the correct step at this point, as we will do that in the Boundary Condition Manager. For now, activate all the boundary conditions in the Make Contact step. Now let's tell Abaqus which steps these boundary conditions should be activated in. Right-click on the BC's container in the model tree. Choose Manager. The press plank curved and press rect plank become active during the Make Contact step, where they displace the parts closer together to establish contact. However, they must not be active in the Apply Force step, hence they should be deactivated using the Deactivate button. We would like Fix Curve Block to be active starting from the initial step or the Make Contact step. Both should work the same, but I prefer putting it in the initial step, since in reality this constraint exists from the very beginning. The boundary condition will propagate to the remaining steps. We can use the Move Left button to move the boundary condition to the correct step. Fix Plank End and Fix Rectangular Block are required for the Apply Force step. Click the Dismiss button to close the Boundary Condition Manager. Let's create the load. We'll call it Concentrated Forces at Corners. Activate it in the Apply Force step and set it to type Concentrated Force. Abaqus prompts you to select the points for the load. Select the two corner points at the bottom of the free end of the beam in the viewport. Give the concentrated forces a magnitude of 4 million newtons in the negative y direction. Note that this force is applied at each node, so since we have two nodes, that gives us 8 million newtons. We need to identify and name the surfaces that will come in contact so that we can specify the contact interactions. Let's create some surfaces. Expand the assembly container in the model tree and double-click Surfaces. Name the surface Rect Block Bottom. It is hard to select the bottom of the rectangular block in the viewport since the plank is underneath it. One way to make it visible is to temporarily suppress the face-to-face constraint between the rectangular block and the plank. In the assembly container in the model tree, expand Position Constraints. Right-click on the appropriate face-to-face constraint and choose Suppress. You can now create the surface as you can select it in the viewport. Now resume the surface-to-surface constraint. Create another surface called Curve Block Top using the top surface of the curve block. Create a third surface called Plank Bottom using the bottom surface of the plank. And create a fourth surface called Plank Top using the top surface of the plank. Now let's define the contact interaction properties. Double-click Interaction Properties in the model tree. In the Create Interaction Property window, name the interaction property Frictionless and set it to type Contact. In the Edit Contact Property window, click Tangential Behavior in the Mechanical menu. Set the friction formulation to Frictionless. Click OK to close the window. Let's define another contact interaction property. Name it Frictional and set it to type Contact. In the Edit Contact Property window, click Tangential Behavior in the Mechanical menu. Abaqus uses the Coulomb friction model for frictional interactions. Ideal friction behavior requires for two surfaces sticking together to remain that way till the shear stress exceeds the critical shear stress, and when that happens, they suddenly start slipping. However, this ideal behavior is difficult to simulate, and Abaqus provides a few other options. It is usually advisable to use a penalty friction formulation. This formulation allows a small elastic slip even when the two surfaces should be sticking. Abaqus will automatically choose the penalty stiffness such that this allowable elastic slip is a very small fraction of the characteristic element length. The static kinetic exponential decay allows the user to specify static and kinetic friction coefficients. In this friction model, the static friction coefficient decays exponentially to the kinetic value. Test data can also be entered to fit the exponential model. In addition, you have the option to specify elastic slip. If you wish to enforce ideal frictional behavior, go with Lagrange multiplier. With this formulation, there will be no slip between the surfaces till the shear stress has crossed the critical shear stress. The rough formulation specifies an infinite coefficient of friction, meaning that there is no slipping between the surfaces no matter how high the shear stress. And user-defined allows you to specify the shear interaction with user subroutines. Set the friction formulation to penalty. You see three tabs: friction, shear stress, and elastic slip. Let's focus on the friction tab. Leave the directionality set to the default of isotropic. This tells Abaqus that a uniform friction coefficient should be applied in all directions. Anisotropic allows for different friction coefficients in the two orthogonal directions on the contact surface. The options for slip rate, contact pressure, and temperature-dependent data do as their names describe. They allow you to tell Abaqus whether or not the friction coefficient is dependent on slip rate, contact pressure, or temperature. We will leave these options unchecked. In the table, we shall set the friction coefficient to 0.1. Let's turn our attention to the shear stress tab. You have two options for the shear stress limit: no limit and specify. No limit tells Abaqus that the shear stress does not need to exceed some critical value for the surfaces to slide. With the specify option, on the other hand, you tell Abaqus the shear stress limit. When the magnitude of the equivalent shear stresses reaches this value, sliding will occur regardless of the magnitude of the contact pressure stress. We shall leave the shear stress limit set to no limit. Now let's consider the elastic slip tab. Since we are using Abaqus standard, we can specify the maximum elastic slip. Fraction of characteristic surface dimension allows the user to specify the maximum allowable elastic slip as a fraction of the characteristic contact surface length. Absolute distance allows the user to enter the absolute magnitude of the allowable elastic slip. We shall leave fraction of characteristic surface dimension set to Abaqus's recommended value of 0.005. Click OK to close the window. We now have two interaction properties, frictionless and frictional. Now that we have created surfaces and interaction properties, we can proceed with creating the interactions. Double-click Interactions in the model tree. Name the interaction Curved Plank Interaction, as it will define contact between the curved block and the plank. Click Continue. Abaqus prompts you to select the master surface. You can select the surface in the viewport, but we've already created surfaces, so click on the Surfaces button. In the Region Selection dialog box, select Curve Block Top and check Highlight Selections in Viewport to see the section highlighted. Click Continue. Abaqus then asks you to choose the slave type. Choose Surface. Once again, you see the Region Selection dialog. Choose Plank Bottom and click Continue. You see the Edit Interaction window. Here, Abaqus tells you which surfaces you chose as master and slave and gives you the option to switch them. Let's talk about why we chose these options. There are two types of contact discretizations in Abaqus: node to surface and surface to surface. In node to surface, the nodes on one surface, the slave, contact the discretized segments on the other surface, the master. It is not possible for the nodes of the slave to penetrate the discretized segments on the master, although the nodes on the master may penetrate into the slave surface. For this reason, the choice of master and slave is important. The surface you select as slave should be the more finely meshed surface, and if the mesh densities are similar, the slave surface should be the one with the softer material. The surface-to-surface contact formulation, on the other hand, considers the shape of both the master and slave surfaces in the region of contact, and enforces the contact conditions in an average sense over regions near the slave nodes rather than on individual slave nodes alone. Large penetrations of master nodes into the slave surface do not occur with this discretization. Hence the choice of master and slave is not as important, but the same surface selection guidelines as node-to-surface discretization should be followed where possible. Since node-to-surface discretization simply resists penetration of slave nodes into the master surface, forces tend to concentrate at these slave nodes, which leads to spikes and valleys in the distribution of pressure along the surfaces. Since surface-to-surface discretization resists penetrations in an average sense over regions of the slave surface, this has a smoothing effect. Generally, surface-to-surface discretization provides more accurate stress and pressure results. However, it also involves more nodes per constraint and can therefore be more computationally expensive, although in most applications this extra cost is fairly small. Although surface-to-surface provides more accurate stresses than node-to-surface, as the mesh is refined, this discrepancy becomes less. Abaqus Standard offers two tracking approaches that account for the relative motion between two interfacing surfaces: finite sliding tracking and small sliding tracking. Finite sliding allows for arbitrary relative separation, sliding, and rotation of the contact surfaces. The connectivities of the currently active contact constraints get updated based on relative tangential motion of the contact surfaces. Small sliding, on the other hand, assumes there will not be much relative sliding between the surfaces. The connectivity constraints between the nodes involved remain fixed throughout the analysis, although the active-inactive status of the constraints can change. Small sliding tracking is based on linearized approximations of the master surface per constraint and is computationally less expensive. However, your assumption of small relative sliding between the surfaces must be valid, or you will get incorrect results. You see 4 tabs: Slave Adjustment, Surface Smoothing, Clearance, and Bonding. We will not be changing these options in this example, but I would like to familiarize you with them. Slave Adjustment adjusts the position of the slave surface of a contact pair. Slave adjustment is useful in eliminating gaps or penetrations caused by numerical roundoff from graphical preprocessors such as Abaqus CAE. These might cause convergence issues during the analysis, and slave adjustment can be used to move the slave surface in order to minimize or get rid of the gap or penetration between the surfaces. The adjustment made by Abaqus will be strain-free. It is recommended to adjust contact surface pairs when using small sliding contact. Mesh discretization, especially a coarse mesh, causes inaccuracies during the contact calculations. When automatic surface smoothing is selected, Abaqus can identify axisymmetric or spherical surfaces in the contact pair and smooth them. Clearance allows you to specify an initial clearance between nodes on the slave and master surfaces when using the small sliding formulation. For initially bonded contact conditions, bonding allows you to restrict cohesive behavior to a subset of slave nodes. For the contact interaction property, choose frictionless, which we'd created earlier. Click OK. Create a second interaction called rectangular plank interaction, as it will define contact between the rectangular block and the plank. Set rect block bottom as the master surface. And plank top as the slave surface. This time set the contact interaction property to frictional. All that's left to do now is mesh the parts and run the simulation. Mesh all 3 parts using 8-node linear brick reduced integration elements and an approximate global size of 4. Create a job called Contact Simulation Job and run it. Let's view the results to make sure everything ran correctly. Plot the deformed shape in the viewport. You see the expected behavior. The plank successfully contacts the curved block and bends along it. The rectangular block, on the other hand, holds the other end of the plank in a horizontal position just as it should. Let's look closely at the contact pressures. Plot a color contour on the parts. By default, the mesos stresses are displayed. Change the primary variable to contact pressures or C-press. You can see color contours on the plank and the curve block. The presence of contact pressures indicate that contact has occurred. Since we made a special step, make contact, just to establish contact, let's make sure that contact did actually occur in that step. Bring up the frame selector tool. Move the slider to observe when contact pressures appear on the plank and curve block. It would appear that contact pressure is present on the plank in both the make contact step and the apply force step as expected. However, there does not appear to be contact between the plank and the curve block in the make contact step. It is possible that the contact pressures are much higher between the rectangular block and the plank than between the plank and the curve block, and the range of the color contour is too large to indicate subtle differences. So let's remove the rectangular block and the plank from the display. Use the Replace Selected tool from the Display Group toolbar. In the prompt below the viewport, choose Part Instances as the entities to replace. Click on the curve block to select it, and then click Done. The curve block replaces everything else in the viewport and is the only part displayed. Now we move the frame selector slider again. In the last increment of the make contact step, you see contact pressure is displayed on the curve block. This confirms that contact was established in the make contact step, even though these contact pressures are a lot less than that between the rectangular block and the plank. Use Replace All from the Display Group toolbar to replace the current view with all of the parts. This concludes the contact tutorial. Contact is a complicated subject, and as you can see, there are many options you can play around with. Convergence issues are frequently encountered when contact interactions occur. The Abaqus documentation is your friend when dealing with the subject.